Hi, everyone, and welcome. I'm glad to see so many of you registered for this topic of steel design, which is also my favorite topic. Um, as you can see by the time on my window, this is a pre-recorded session, so I'm recording this 2 days prior to this webinar, so that on the day of the webinar, I can be also at the same time present to answer your questions that you might have into the tab. So this is the usual working of the GoToWebinar at SCIA Engineer, where you guys are muted during my presentation, but you will find a question box where you can type whichever questions come to your mind, and I will be able to answer them in real time. Like always, the session is recorded and you will find it on YouTube afterwards, so you can share it with your colleagues or you can watch again some part that was particularly interesting to you. All right. The aim of this session is dual. So I want to, on the one hand, for new users or beginning users of SCIA Engineer, give an overview of the possibilities for steel design in SCIA Engineer in general. And on the other side, for also new but equally for advanced users, I'd like to give some details on the latest developments that we made for steel design in version 24 of SCIA Engineer. I will try to put the info on the new functionalities in the beginning of the presentation, and I will tell you guys when I've reached the final topic of this, so that in case you are no longer interested in the rest of it, you can leave or you can stay and maybe learn something new about SCIA Engineer. I'll leave that part up to you. And with that, let's get started. So let's maybe just start by creating a new project so I can give you the start on the very beginning of the steel design. Of course, we're going to select the steel material, and just under it, you can select the default material that will be used throughout your project. That doesn't mean that you can only use this one material. You can use all the materials you want inside the project, but this will be the default selected. And here you can find a list of Eurocode materials. Why Eurocode? That's because we have, of course, the Eurocode selected here for our project. But SCIA also supports steel design for a number of other codes, being the Brazilian code, the American code, and the Swiss code. And as you can see, there is a little sneak peek in here. We also are currently supporting the second gen design for the next generation of Eurocodes, but it's not yet available in version 24 unless you have a special license. If you are interested in a webinar where we would show you this development and show you the changes that have been made between the current and the next gen Eurocode, more into code detail rather than a SCIA detail, do let me know either in the questions box or in the comments of the YouTube video. And if there is enough enthusiasm, we can make this session happen. All right. For this one, I'm going to stay with the Eurocode because most of the registrants and our users are using the Eurocodes principally. So let's choose the Eurocode. And of course, we also select a support most of the national annexes. If you do have an annex that's not supported in here, it's always possible also to create even a new national annex. You can call it new. You can base it on one of our existing national annexes. Let's base it on the standard EN, for example. We call it new again. And then you can actually go into, let's say, the settings for steel and adapt the values as you wish for supporting your special national annex. So this is also a possibility. But for now, let's just say we are going to take the Belgian national annex because I'm Belgian and work with this. Okay. So the first thing you might do when starting a new project is to go into the cross sections menu, which is where I will also show you the first one of our new developments for version 24. In this menu, you will find a whole catalog of sections in the profile library, where you can select the shape of section you are looking for, and then for each section, there is a list of available catalogs. Uh, Once you select one of those, you will see the reference to the database or catalog it's coming from, and then you can go to the list of available sizes and select your profile. Or if you already have a specific profile in mind, you can just type in the name of your profile, like IPE 160, for example, very typical, and you can add it into the project. Of course, there is a numerous of other options. We can have paired sections. Be careful when you select these. They will work together as if they are fully connected. But we do support checks for this as well, for these kind of sections that are linked together. You can have some closed, some hunches, some welded sections, some sheet welded sections. And then we also have some thin walled geometrics where you can yourself add in the sizes of your section and change its shape and parameters. Later, I will show you that you can also optimize these parameters in the steel design. But I was going to show you the novelty. It's a small one, but it's there. Let me get to, for example, IPE. Yeah, there we go. We have updated our profile library catalog for ArcelorMittal. So ArcelorMittal has provided us with their latest catalog of version 2023, and we have implemented it into SCIA Engineer. In case you are looking for a catalog that's not yet available in our software, do send us through the information, and maybe we can add it for a next version also. Okay, and if all of these options are not enough for you, then you can always use the, where is he? He's hiding for me. General. Okay, I'm blind. Oh well, so you can always use the general section option, which is a very, very powerful tool. It allows you to either import any kind of drawing from DXF or DWG format, or you can draw in yourself a section, or you can load in sections from the library and combine them in any way or shape that you would like into the software, and then the software will calculate behind it all of the parameters. If you import the section as a thin walled representation, so with center lines, then it's also possible to calculate effective sections and buckling properties of the section. If you input it in a polygon kind of way, so the full surface is drawn and not just center lines with thicknesses, then you can still use the option called thin walled representation, where you draw the center lines over your section, and then this drawing is used for the effective section design. Okay. Close. I don't want this. Okay. And then let me get on to the project I had pre-made. I didn't really optimize it or anything. I just drew on some things. Let me get into this shape, for example. So, because one of the second new developments for version 24 is an option to add in this restraint by sheeting. So this is an option that will be available for all asymmetrical profiles. So for all the profiles that are doubly symmetrical, you will not find this option only for asymmetrical profiles. Why? Because for symmetrical profiles, actually the local axis of the section will align with the principal axis of the section, and so this option will not make any sense, because this option actually will force the checks and the output to be done according to the local axis of the section rather than the principal axis of the cross-section. So normally checks are always executed according to the principal axis, as stated in the Eurocode. But there are some cases where this is unwanted behavior. For example, if you have some L-shaped section that is attached to sheeting, it will not be able to move along its principal axis or buckle along its principal axis because it is fixed to the sheeting and can only move in the local axis directions. And therefore, it only makes sense to do the check in the local axis and be a little more economical. And that's what this option does. So if you activate this, you see that the software forgets about the fact that there is a turned local axis, and he will just pretend also for the calculation that the principal axis and local axis are the same. So even in the results, if you ask for results according to its principal axis, it will just give you results along the local axis. And if you go to the steel design, for example, or steel ULS design for my current selection, let's give you the detailed outputs and give a preview. Then you can see that in the output, there will be a note stating that the cross-section is restrained by sheeting and thus will bend only along its local axis system, and therefore we will ignore the rotation of the principal axis system. You can also see that this was a cold form profile and therefore the cold formed code check is executed. Of course, this also works for the normal steel check. Okay, and then I will skip a bit illogically in our steel design, but present you our final improvement for version 24, which is in the steel SLS design. Let me just select one frame instead of doing it for the entire building. Okay, and refresh the results. Of course, first we would check the overall unity check in a normal world. So of course, this is our ULS design. You can have checks based on limit settings that are set globally in our steel settings or locally per member. You can make some different limits for the deflections that are tolerated. And then the actual deflection will be compared against the limit deflection. What's also possible is to make a different limit for the variable loading and introduce some camber, either manually or let the software calculate which camber is necessary to make the structure pass the check. So what has been newly developed for the SLS check is a possibility to display the relative deformations of the elements, not only in the usual way where we had just millimeters of deflection, but in a relative way, being these millimeters divided by the length of the respective beams. So if you go here to values, you will see that you have all the values, and then the values are repeated with the little rel indication behind them. Rel meaning that they will be expressed in a relative manner. So if I select one of those, we will see actually there are the same values, but they are displayed in a relative way. So the millimeters are divided by the length of the beam and then expressed in a fraction form. In case, I don't know why, you would want to display it in a fraction instead of, in a, how do you call it? a decimal number rather than a fraction. It's also possible you can change this in our unit settings over here. You can manage the units, and there you can choose the type of display you want for this relative unit. But I think the most practical part is to have the fraction visualization, because this at once gives information about the deflection of the respective beams and gives you an indication of how far they are from the limits. And then in the preview, you will see that now the preview has grown a little bit, and all the values are displayed both in the millimeter version and in the relative version. As you can see, each value is doubly displayed in the two systems in the report. And of course, you will find the unity check and camber if you have defined some camber. And this leads me to the end of what is new for steel, specifically for version 24. I will continue to give some more overview and introduction on what is possible for steel design with SCIA Engineer. So do please stay if you are interested. And if not, nobody shall blame you. Okay, thank you for being here if you are leaving. And yeah, so as you can see, it's pretty intuitive to get results and unity check, as I already displayed you previously for this one beam. If I do the design for my entire building here, let's say ULS design, I want to have the global extreme. You will quickly obtain some results. Of course, here 544 items, beams have to be calculated for all of the combinations that I have defined, and the check is executed. So it's not a lightning speed, but it goes rather fast. And once the checks have been calculated, one of the strongest parts of SCIA Engineer is the possibility to give you very detailed outputs on all the values and how they were obtained. So I already showed you the detailed output in the tables version, but we also have an option to print out formulas, or both tables and formulas. And if I do this, refresh and show the preview, you will see here, this one is the normal code check. So the most limiting member seems to not be a cold formed one. You can see the safety factors used, the material strength used, the forces that are present for the limiting case, the classification of the cross-section for these forces and what it's classified as. And then each check is printed with all of the values used in the formula printed with their values. So it's super transparent. Every formula is linked with a reference to the code. So there really isn't any unity check that you cannot double check behind and manage to find where it comes from in the end. Yeah, so it's very, very easy to obtain results with SCIA Engineer and to have designed some steel design for your model. But do be aware that there are some things that you as a user need to think about. Most of the settings go automatically and you automatically get to some results, but some of these settings need to be reviewed for you to have results that actually make sense. And mainly in this part, I'm talking about the buckling settings. This was a linear calculation that I've done. So we have results for a linear calculation, and therefore for the buckling design, some buckling factors are used. And our software calculates these buckling factors based on the analysis. It will define rotational stiffnesses in the nodes of the beams. And then from these rotational stiffnesses, it will try and find a possible buckling factor. But these values do need some human verification. It's possible also to display them. Let me print here the KY values. I need to have a selection. Let me select this one. Okay, yeah, so here you see already we get to some buckling factor of 10, which is, yeah, probably too high for this type of column. So it's important to keep in mind to verify the K factors that come out of the simplified calculation, and either yourself through the buckling settings of the member, which I will show you now, define some buckling factors for all of your columns and types, or for the ones that are not accurate. So here you can set the buckling factor to a factor or a length if you prefer a factor, and you can enter a factor that makes more sense according to your design. You can name this group principal column, for example, and you can expand these two other areas. So, for example, my column on the opposite side, where are you? This one, I can give it the same buckling group of principal columns, and this is how you can construct some buckling settings for all of your building. The philosophy of our software is to get you to the result fast by using smart defaults. For example, like the buckling factors, we try our best to give some first estimation on the buckling factors so that immediately a steel design can be performed without you needing to manually give buckling factors in everywhere. But we also don't want this to come at the cost of what you are able to do with our software. So we have plenty of places where these default choices can be overruled, either globally for the entire model, which can be done in the steel settings for example, for methods that are used in the calculation. For example, here for the classification, we offer the possibility, and by default they're turned on, to use some complementary research to the Eurocode that leads to a little more economical results than the pure Eurocode itself. But as a user, you can always choose to deactivate it if you want to purist use the exact Eurocode as it's written. You can turn them off. Also, for example, for lateral torsional buckling, you can choose different methods for the C factor calculation, for example. And also, I think most used are these general settings where you can set to have an elastic verification purely. So where you will ignore any plastic deformation. So you will only allow, allow the structure to move through the elastic region of the material and not leave room for any plastic effects. And only elastic resistances will be used in the check if you turn this option on. For example, the next one will ignore any stability checks and only execute the section checks. If I activate it here, it's done for the global model, but I can also decide to do this member per member. For example, I have activated it on my, um, I don't know what they're called in English, but yeah, these braces here, they are set to section checks only because, for example, in the linear calculation, they will get some compression and they will buckle out immediately and lead me to some very high unity checks, whereas this is, yeah, not a problem to me. So therefore, only section checks are verified here. Also out here, you can set, for example, settings for the fire resistance. If you are going to do a fire design of your steel, you can set the required resistance time, the temperature, time domain, and all of these topics. And also for the SLS deflection check I was talking about earlier, you can set the limit values for the relative deflection under the total loads and under the variable part of the loads for both the directions of deformation, and also you can set the design of camber or an input value for camber that you would like. All of these settings can also be done locally in some shape or form. By applying steel member data to an element, here you can set the elastic verification or the section only checks, or you can even overrule the classification of a member that has been done by the software. Of course, class 4 is not possible because there an effective section would be needed, and how would we calculate an effective section if it's not really a class 4 section? It's quite impossible. So only these three classes can be manually overwritten. Other things that you will find here in the list are these links that I've talked about earlier. The links are for these double sections to create some patent compression members, and also SCIA can effectuate the check for those patent compression members. Some data for local transverse forces checks of cold form sections. You can add some stiffeners for the web. You can add sheeting that will provide some additional support for lateral torsional buckling, and you can add LTB restraints. Finally, this one is to allow to calculate the buckling factor from a stability calculation. So you will do a stability calculation, find the critical force, and then the software will calculate automatically the corresponding buckling factor for your member. So these are all of our settings. And then finally, in the menu we've seen before, which are the buckling settings here, you can set everything that's related to buckling, also torsional buckling, lateral torsional buckling, and local settings for deflection. By default, the program will recognize all the points that are restrained for buckling and give them a full triangle, and all of the nodes that aren't will have this half dashed line. I can myself override this just simply by clicking. It will change the settings. And if I go look at the other axis, you will see that here there is no beams supporting the buckling of our column, so they are shaded out. If I do want to add a support that's not in my model, I just click. And you will see also on the side where you can set the K factor that the span is split in two, and you can set a K factor for each of the new spans. And for deflection, you can do the same. You define the points in between which the relative deflection is calculated. And then per span, you can set, if you want, a different factor, a different limit for the deflection. So either if you follow from setup, you will have the same values as in the setup, but you can also say that I want to change my values for all the spans or per span. And also camber can be defined locally, so member per member if you would like, or group of member per group of members, because as you remember, these settings can be shared over multiple elements. So this is our buckling dialog, and actually your local setting for system length, support points, and all of the local settings on deflection and buckling. Okay. I think that was quite an introduction already. Let me go back to our steel ULS check for my current selection. So maybe another member will give me some higher results. Okay. And of course, I've shown you the detailed output. We also have a summary output, which looks a little bit shorter. We make sure that it always fits into one A4 page, and it gives you some quick overview of every check, the design force, the resistance force, and the unity check that it leads to. Also for the stability checks, the used buckling factors and critical moments are printed out, the slenderness, and then the checks are given. They are grayed out if they are very low values, green if they are okay, and red if they are not. And this kind of output is good to give to some checking agency rather than having them read the 15 pages of formulas. They get all the info they need right here in just a one-page format. But also for you, if you're wondering which of the checks is failing, instead of going to the 15 pages, you can look here for each check what the value is, and you can see which the limiting check is for this member. And then finally, we have a brief output. Generally, this one is used for printing the details of all the beams because it will just give you the results in one single row per beam. So if all of the beams are selected, you will have a row per beam with the overall unity check, their section check maximum, and their stability check maximum. Okay, so as I can see here, my beam is quite over-dimensioned. And SCIA also offers the possibility to do an auto design and automatically find the most economical section for this situation. This can be done automatically by using the auto design function here. Okay. We need to switch the filter to cross-section. Let me just check which cross-section I had here, the IPE 100. Here, I will refresh the check. Okay, so that's all the places where my IPE 100 is used. It's still not used. It's still not overused. So let's see if we can find a more economical option. I will search for the optimal one where I can set the limit of the maximal check to be 1. And he goes through the list of my section catalogs. You can also choose to sort the list by different settings. So for example, here I have optimized for the height, and maybe I want to optimize for the area. So let's try again. Comes with the same result. So okay, let's select this one. We can refresh our check. And now it still passes, but I'm using a slightly lighter profile. Now, if you don't want to use this automatic kind of design, there is also some possibility to log the results. Because if you change a cross-section in a model, then actually the calculation has to be done again to find new results because you have different stiffnesses. But if you want to prevent this happening while you are changing multiple of your cross-sections, and only after you've optimized all of the different ones, rerun the calculation, you can do this by locking the results. You will get this red square telling you that the data is currently outdated and that a calculation is required again. Um, but you can go ahead and make your changes and still ask for results for other cross-sections and change them without the results getting deleted, which is quite a practical option. Now, I've showed you the auto design on the local level, so cross-section per cross-section. Oh, that's the wrong button. I meant to deactivate this one. Yeah. Okay, there's also an option to do a global auto design routine, which will auto design whichever cross sections you select. So you can add for steel cross section auto design. Okay, you can add all the cross sections you want to optimize. And then actually the program will calculate, find the optimal section for each of them, then recalculate, then refine the optimal section until after some iteration he comes to the same solutions twice, and then he will give you a return with your newly designed sections. I will not do it now because it would be slightly boring to watch the routine go, but surely if you do it yourself, it's the perfect time to get a coffee. Now, as you can see, I had changed some cross-section, so my results are gone. I can quickly relaunch a calculation. I'm nearing the end of my allotted time, So I think I cannot show you much anymore, but what else is possible with our software for steel design is connection design. So only for the connections described in the Eurocode. If you are doing any kind of connections for which no design is prescribed in the Eurocode, we do offer a link to Idea Statica, where you can calculate any type of connection, or you could create some finite element model with plates in SCIA Engineer itself. There's some nice video about this also on our YouTube channel on how to do this. We also have a specialized option for scaffolding where you can check the couplers, and a special check is done for the scaffold members. And it's also possible to define some openings in your steel elements and still do a calculation and design with those options. Yeah, if some of those topics interest you and you would like to have some detailed webinar or longer webinar on those, do let me know and maybe I can plan that in the future. I hope it was interesting for you. I hope it gave a good overview of what the capabilities are and what the things are that you do need to keep in mind if you are doing steel design with SCIA Engineer. I hope you learned something, and I hope to see you next time in another webinar. Thank you guys for listening to me.